Good morning and welcome to this recording. The recording is for chapter 20. This is really the culmination of the entire 4 chapters dealing with thermodynamics. So in this chapter we're going to discover some key concepts. The two main ones are the concept of an engine. Make sure that my pen is writing. So we need to have the concept of an engine. Which is really a cycle in here that we start from a PV diagram, from point in the PV diagram, and we come back to the same point. This is in contrast to the concept of a refrigerator, which is just an engine working backward. Okay, so that's the idea behind the two. And then the other concept that we're going to be exploring in this chapter is the concept of entropy, which is something that we will need. For that, for the entire thing, it's really laying on top of something called the second law of thermodynamics. This whole idea of thermodynamics actually was started by thermodynamics Carnot, who asked the simple question: what is really the most efficient engine that I can conceivably have? He did that while he was working as an engineer with the French army in working on trains. So that was in the early 1800s, around 1824. And in doing so, he basically came up with the second law of thermodynamics, formulated not in its modern format, but at least in the first format that he came up with. As I mentioned before in the past, that this whole branch of science was discovered backward. In a sense, the second law was discovered first. Then the first law was postulated later on, some 20 years later, when it was postulated, to put it in context, because the first law, really the one that we just discovered from chapter 19 deals with the energy and the conservation of energy, and it's probably more fundamental than the second law. Then people realized that they need a way of measuring temperature, because this whole thing relies on it, so they formulated the zeroth law because they couldn't move things around. So anyway, these are some historical effects stuff that hopefully you guys are at least that's part of your common knowledge, if I should put it this way. Anyway, so let's get going. So let me remind you what a PV diagram looks like. I know that we've been talking about this one several times before in the past. So let me draw what a PV diagram look like. Again, I have a volume in here, and I have a pressure in here. I know this is not the best drawing that you probably are going to see in your lives. On the PV diagram, because we have PV equal to nRT, I can always fix T's and draw this function P as a function of V, which is just a 1 over X function. So these are called the isothermals. I'm going to pick up two isothermals on particular thing. So this one is happening higher than the first one, so this is TH, this is some T cold. Okay, one of them at a higher temperature than the other. So those are my isothermals. Does the engine or the refrigerator use them? It doesn't matter, as long as the engine or the engine is going to be counterclockwise, so in this direction, operates between these two temperatures. I'm supposed to have it like this. We have these two H's. In between them, there are some temperatures in between. Okay, so we don't care about those. The main things are the TH and the TC. So it is an engine if it is going clockwise. Okay, the work is going to be negative if it's clockwise. Okay, that means that it's energy coming from the gas to the environment. That's what negative means. That means the engine is losing energy in the form of work in that way. Okay. If the process is backward, if the process is in the opposite direction, meaning that it's counterclockwise, I know we've dealt with this sign a lot. The work in this case is going to be actually positive. So in other words, the work in this case needs to be supplied to the quote-unquote engine in this situation to do the other process around, extract heat from the cold source and dump it on the hot source. So that is exactly how the refrigerator works. Refrigerator, you have to plug it to some power, and then what it does is you put something cold at room temperature. It makes it even colder than room temperature and dumps the excess heat into the environment. Okay, the engine works the opposite way. It takes heat from the hot source and does something beneficial for you, which is work in this situation, and the work and dumps the exhaust into the cold source, and then completes the cycle. So that is really in a nutshell what how the process works. The work in the case of the engine, it's this area actually. That's what the work is, enclosed by the cycle. This is a cycle, of course, if it closes on itself. It's a process if it only goes from one point to the other, but if the process somehow finds another process so that it completes the cycle, then in this case we really have an engine if it's clockwise. If it's counterclockwise, we have a refrigerator. So that is the concept that we are dealing with. So obviously, going from TH to TC, you can go through different processes. We already discovered 4 of them. The isothermal will not take you from one to the other. The isothermal will stay on the same temperature. So you need at least an isochoric process somehow, or 2. You can need at least an adiabatic process, or 2. You will need probably an isobaric process, or 2. To take you from one point to the other, so that you basically complete the cycle. And that's really what makes the full distinction. Obviously, you can go in this weird path and come up with your own. So it doesn't have to be one of this well-known paths, as long as there is a way of doing a process that takes you from TH to somehow TC. That is what we call an engine. Okay. So an engine can be conceptually can be made according to the following plan. So basically, I have a heat source in this case, TH. Okay. So think of this one as some sort of a sink, in that it doesn't sink. Is it sink? Okay, I need to. No, I'm sorry. That's not the sink I meant. Okay, not the synchronization. I meant a sink, like the one that you use in your kitchen. Okay, so that's the one. Okay, so in a sense, this is a reservoir. It's used also. Okay, the word used for it is a French word, which means, I don't know, reservoir, where you put stuff in. Okay, so imagine this one never runs out of this TH. It always maintain its TH. Okay. Another kind of reservoir sitting at a lower temperature is TC, like room temperature, for example. No matter how much heat you put in it, its temperature doesn't change. Okay, so that's basically, at least through the thermal processes. So that's basically how the engine works. You take heat, QH, from the hot source. You do work, okay, W, and you have to dump some heat to the cold source. So that's basically how the engine works. So the usefulness, if you wish, of this engine is this work. So this is what is used for. This is how you define, in this case, the usefulness of this engine. So what you do in this case, by definition, the efficiency of an engine is the ratio of the useful thing. Remember, this number is negative, so we have to take it in absolute value, okay? Divided by the cost, what costs you to do that, and that is you have to have heat. So, for example, if you are doing an engine, a car engine, you have to go and buy actually gasoline that costs you money and put it in the tank, which is extracted from the tank and heated up, basically used, fired. And then that gasoline is what costs you really to do that. So it's coming from the hot source. QH in this case, I can really ignore putting it in using the absolute value, because it's going to be positive. The point being in here is, by conservation of energy, by the second law, we can clearly see that the net work, the net heat that you're going to take it, part of it is going to be, I'm taking it in absolute value, of course, and part of it is going to go to QC. Okay, so this is simply the first law. So where is that work coming from? It must come from the source, which is in this case the hot source. Where is that the excess, if you wish, the difference, because this is not going to be equal to that, and we will see why. So the excess is also must be coming from that. So that's basically what, in a nutshell, what the efficiency is. You find it usually written this way. Okay, so in a sense, I can write W as just being the difference between these two positive values. I mean, I took the other one in absolute value because QC will turn out to be negative. So if I do that, then the efficiency, is simply the ratio of these two the difference over the. So it's going to be QH in absolute value, if you like. It's going to be positive anyway, minus QC. This has to be an absolute value divided by QH. So numerically, this is always equal to 1 minus QC over QH in absolute value. Okay, so this is by definition what the efficiency is of an engine, how useful it is. If it is the other way around, if it is a process that is a refrigerator, then the usefulness in this case is how much heat you extract from the cold source. Okay, and what costs you then is the work that you have to do. So that has a different parameter for the refrigerator. I'm not really going to emphasize a lot on the refrigerators or the process, because the integration will just become in the opposite direction. That's it, and the negative become positive, and the usefulness in that case is not an efficiency, but is a different parameter for the refrigerator. Okay, so I'm going to leave that for you guys to read it through the book, because it's really not hard to extend this concept to a refrigerator. So that is basically how the efficiency is defined. So why in the world do we need this QC? Why can't we just take heat from the hot source and do work with it, and end of the story? That would be 100% efficient if W is equal to QH. If W is all the heat that we take from the hot source will basically become work, then we have an efficiency of 100%. And that still doesn't violate this law, because if QC is equal to 0, obviously QH is equal to W. So the first law would tell us that this is possible, that there is no problem with having 100% efficiency. However, the second law will prevent that, and that's really what the trouble is. So thermodynamics is kind of a sad story, really, if you think about it this way. The first law says that the best thing that you can do is break even. In other words, W will be equal to QH. The second law will come into play and state the following, that you cannot even do that. You're always going to have work that is less than what it costs you. So the efficiency will be less than 1. So that's really where the problem is, because QC is a must. You have to operate between two temperatures. So that is really what the essence of this whole thing is. So let me put it in simple terms. How so this is the first law. The second law. How Mr. Carnot put it. Okay, grant me the following, because this is what day in day out observation dictate, that heat cannot naturally or spontaneously, okay, flow from a cold source to a hot source. That would be weird, actually, if this is true. I mean, imagine yourself, you take your cup of coffee hot from the coffee machine, and you put it in room temperature, which is a lot colder. Your cup of coffee is boiling at 100 degrees Celsius, and the room temperature is sitting at 25 degrees Celsius, for example, room temperature during a hot day. Hey, then all of a sudden, the cup of coffee starts to even increase its temperature as it gets warmer and warmer. That's not possible. Usually it's the other way around, that the cup of coffee its temperature will go down. So in other words, if I put two heat sources, one sitting at TH and one is sitting at T cold, heat will always flow from the hot to the cold. That is what this statement is on its own, spontaneously, okay? So don't tell me about the refrigerator, what's going on in the refrigerator, because the refrigerator takes heat from the cold temperature and put it in the hot temperature. That is because it's not a natural process. That is because we're adding work to it. but on its own spontaneously, if I take a hot cup of water, it's going to get cooler if I put it in a cool environment. That is how heat flows. So this is the second law, basically, of how Mr. Carnot formulated it. He said, if you grant me that, I'm going to come up with the most efficient engine. Okay, and the engine that he came up with is called Carnot cycle or Carnot engine. Okay, so let's look at this cycle in here and see how it looks like. So Carnot cycle has 4 strokes, or 4 processes if you wish. Again, it's operating between 2 temperatures. This is the volume, this is the pressure, this is TH, and this is T cold. Okay, we start from point A in the process where the volume is VA and the pressure is PA. We go through a thermal expansion at constant temperature. So this to point B, we are expanding, so there is an expansion in volume going from VA to VB, and in the same time the pressure is going down, okay, at constant temperature. So this is an isothermal process. Then the second one, we're going to go from point B to point C. So this is VC on the second isothermal, where the pressure is PC, and this cycle is an adiabatic cycle. So Q is equal to 0 in here. So this is an adiabatic process. And this is also an expansion. So the system is doing work while expanding from VA to VB, from VB to VC. So the work is going to be negative. However, we're going to go through compression now. To a point which we're going to call VD, to a point D at constant temperature. So again, we're doing another isothermal in here, isothermal, and the pressure of course went up to PD. Then finally we're going to go from D back to A to close the cycle in an adiabatic. So Q is equal to 0 and the last one, meaning that we're doing this adiabatically. So this is an adiabat. So this is how the engine works. So you go through process of expansion. This whole process is done reversibly. That's a key word in here. It's a reversible process. Reversible processes. Okay, so that is a key thing in here. So we're going to expand at constant temperature. We're going to expand at with no exchange of heat. So this is really an adiabatic process. Then we're going to compress at constant temperature from V, did we call this point C? So this is VC down to VD. And then we're going to compress further from VD down back to VA. So we completed the cycle now and we have an engine. So how much work we have in here? This is really the work that we're talking about. Okay, so that's the area of that thing there. That is the work. So the purpose of this exercise now is to find that work and find this efficiency of the engine and show why in the world this process is the most efficient engine if we grant him that heat cannot spontaneously go from the hot source and from the cold source to the hot source. The only way for it to go, if it were to go at all, is from the hot source to the cold source. Okay, so let's find first of all the efficiency. Let's find W basically and find QH. So there is a QH in the process in here. Let me pick up another thing in here. So we have heat being extracted in here from the hot source, so that's my QH, and we have heat dumped in here, that's my QC, and there is no heat in the two adiabats. Okay, so there is no heat in there at all, whether taken or dumped. So that's the only place for the heat. Obviously there is work for the gas to go from this volume, this expansion, and this expansion also. But there is also a negative work in here too. I mean, if you it's a positive, so there is an addition of work in here. So again, I can do the math in here and find this all these W's, but I can just use the first law and just find W is just the difference between these two numbers and end of the story. So I could do that too. Okay, so we could go in very much detail and finding the work in here and finding the work in here, which is just basically integration. And I think we did that in lecture from the previous chapter, but we're going to use just the first law and say that the entire cycle, because there is no change in energy in the entire cycle, because the energy is if I complete the cycle, that's the key with it. There is no change in the energy for a cycle, because the energy is a conserved quantity. The energy is actually a state variable. So if I go from starting point to the end, back to the starting point, the temperature is the same, and the temperature is a measure of that internal energy. So that's why I'm going to use just the conservation of energy to find W, which is going to be just the difference between these two. The algebraic sum, because I know this one is positive and this one is negative, just add the two numbers and keep the signs with the algebra, and you're going to be fine. So W algebraically, and it's going to be a negative number in this case. No, it's going to be a, hold on. So it's going to be QH plus QC. Okay, let me write it down in terms of the energy itself. So it's going to be the change in energy is going to be a Q total plus W, correct? So W is actually going to be minus that. It's going, because this is 0, okay? It's going to be minus Q total, and minus Q total is just QH plus QC. So if I strictly work algebra, ignore about the signs in here, this will come negative, because this one is positive and it's clearly greater because it's happening at a higher temperature, which means this one is negative. So the difference between these two is going to be positive. Because of the conservation of energy, it's going to be negative, which is true in this case because it's an engine. So this area is going to be clockwise. Since it's clockwise, it's going to be a negative area in this situation. If I calculate it, and I'm pretty careful with my calculation, it's going to be properly negative. That's why we work in absolute values, because we know what's going on. We know QH is positive, we know QC is negative, so just take the difference between the two absolute values, and that difference in absolute value is the work in absolute value. End of the story. Okay, so hopefully that's clear enough for you guys that you can do this algebra, whether you do it algebraically, ignore the absolute values, and you're going to find fine. You're going to find the correct answers, or use or use the absolute values, but you need to know what you have. Okay, you need to know the physics basically of the problem if you are going to use absolute values. So let's find this W. So first of all, we're going to find the QH. QH should be easy enough to find. Both of them, QH and QC, should be easy enough. Remember that in an isothermal, delta U is equal to 0. So in going from the first A to B, there is no change in energy because the temperature is the same. It's an isothermal process. So W is just equal to minus QH, and QH in this case is equal to, W is just the integral from VA to VB, and basically I just find the that ratio and I'm done with it. So let's do that quickly in here. So it's going to be the log of the ratio of the two volumes. So QH is equal to nRTH ln of the final volume, which is VB, over the initial volume, which is VA. I think we did this one a couple of lectures before. Okay, so that's easy enough to find the work in that situation, which this is equal to minus the work. So the work will be just VA over VB. Okay, now QC, going to leave this sign if you wish, nRTC, because it's happening at the same temperature, ln of the final volume, which is VD, over VC. And this is why this is negative, because this VD, not VB, I'm sorry. The reason why this is negative is because VD is clearly less than VC. Okay, so the ln in this case is negative. So if you wish, I'm going to convert this one to just minus nRTC ln of VC over VD. Okay, I'm going to show that these ln's are the same. This the VB over VA is a compression rate for this engine. Okay, so we can call it the compression rate, but it's this one also the same rate. So let's see why I'm saying that VB over VA is the same as VC over VD. Okay, let me explain why. This point in here, VB, I mean the point VB and VC are both part of the same isothermal. So what I can say in here is that for B and C, points B and C are part of the same adiabatic, adiabat. So that means that PB, Control Z, that means PV to the power gamma. Let me use the other expression that we found in the lab, actually. Use the temperature instead. So I know T hot where B is, okay? B, remember, is situated on the T hot, okay? T hot times the volume in that point, volume VB, to the power gamma minus 1 is the same point, since the point C is actually on the second adiabat. So what I'm going to write in here is going to be the same ratio as TC times VC to the power gamma minus 1. From here, clearly, I can find some ratios of these two numbers, okay? Let me work on the second expression first, the points D and A. The points DA are two parts of a different adiabat. Let me show you. So the point D and the point A are on the same adiabat, okay? Same adiabatic curve in here. So they too satisfy similar expression for the other ones. So I know the point A is at TH, it's the same temperature, times VA to the power gamma minus 1 is equal to, the point D is on the second adiabat at TC, so VD to the power gamma minus 1. So we use the TV expressions instead of using the PV expressions. Remember, that was part of the lab. Anyway, all I have to do is take the ratio, I'm going to call equation 1, equation 2, take these two ratios and see what I get in here. Obviously, if I take the ratio of expression 1 and 2, the temperatures will cancel because I will have TH over TH and I have TC over TC. So the only thing that remains is the ratio of the volumes. So VB over VA to the power gamma minus 1 is equal to VC over VD to the power gamma minus 1. If I take the ln of both sides, gamma minus 1 comes from the outside, and so I will have gamma minus 1 times the ln of VB over VA is equal to gamma minus 1 times the ln of VC over VD. Cancel the two gamma minus 1. Remember, gamma is always greater than 1, so it's never equal to 1, so I can cancel that. So this ln of VB over VA is the same as the ln of VC over VD. That's my point when I wanted to argue earlier, is that these logs are the same, okay? And VB over VA is actually the same as VC over VD. So that is the proof for that. So now I can find what this efficiency is for the Carnot cycle is going to be. So the Carnot cycle, which is the efficiency for it, is 1 minus the ratio in absolute value, okay? So I'm going to ignore this sign in here because remember, I defined the efficiency now. I'm using this expression, 1 minus QC over QH in absolute value, because I used the expression in here in terms of absolute values because I'm aware of the signs. If I really don't want that, if I want to keep the algebraic expression, I'll have to define it with a plus then, and it's going to be the same expression. Divided by NRTH, this is QH, ln of VB over VA. Again, I just argued that these two ln's are the same. ln of VC over VD is the same as ln of VA. So this 2 will cancel, and the R will cancel, the N will cancel, and for a Carnot cycle, the efficiency is always equal to 1 minus TC over TH. This is a very important expression. So when you're calculating an engine, this is the efficiency of the Carnot cycle, and Mr. Carnot said this is the most efficient engine. For example, an engine that has a boiling room in it, like the old days, can operate between temperature TC, where the exhaust is being thrown out. Let's say, for example, TC is 20 degrees Celsius, and TH is 100 degrees Celsius. So in this case, the efficiency of the Carnot cycle is going to be 1 minus, don't do 20 over 100, that's a big mistake. It's 20 plus 273 over 100 plus 273. You have to be working in Kelvin. That's very important in your expression here. So we have 1 minus, I'm going to do quickly the calculation in here, open parentheses, 293, I guess, divided by 373. So it's 21% efficient, slightly more, if you like, 21.4. Okay, so this one is 21.4 efficient. Okay, what Mr. Carnot is saying is there is no way there is any engine better than this one that can give you more than 21% efficiency in this case. So let's see why that is. Okay, let's see why this is so. Let's see why his engine is the most efficient engine. Remember, this is a reversible engine. Okay, so let's say, for example, we have TH and we have TC, and let's say, for example, we take 100 joules in here from the hot source and dump in the process 80 joules. That's what it costs us to do this, and get only 20 joules out of the process. Okay, so this is a Carnot engine. That's how best it is. And let's say, for example, tomorrow you can come and claim, you say, you know what, I invented a better engine. I have invented actually an engine that takes from the same TH that you're operating with and the Carnot TC. I'm taking the same 100 joules and I'm only getting rid of 60 joules, and my engine produces 40 joules worth of work. Obviously, the efficiency of this engine will be 40%, because 40 over 100 is 40%, whereas Mr. Carnot says you cannot do better than I did, which is 20% in this case. 20 over 100 is 20%. So let's prove that your engine is actually wrong. It cannot be true. Your claim is wrong. You're a liar. You can't do that. And Mr. Carnot is actually more precise and more accurate in his statement. Granted that heat cannot flow spontaneously from a cold source to a hot source. Okay, if that's true, then your claim is wrong. You made some mistake somewhere in there. Okay, since this is a Carnot engine, I'm going to double it. Actually, I'm going to have 2 Carnot engines. So I'm going to build one and build another one for the same thing. So I'm going to have another Carnot engine and connect the two together. Okay, so Mr. Carnot engine operates gets another 100 again joules. So I have 2 of them now, and dumps 80 joules to the TC, and get you another 20 joules. So if I connect these two engines, basically this is how this engine look like. So these two engines, Carnot engines, okay? So I'm still holding you to your claim to prove that you're wrong, okay? So Mr. Carnot engine now is taking 200 joules combined and dumping 40 joules when I add the two engines together, and dumping heat of 160 joules to the cold source. So this is still TH, this is still TC, okay? So this is Mr. Carnot engine. But remember, Mr. Carnot engine is a reversible engine. So what I'm going to do is I'm going to reverse the process. I'm going to go through the cycle in the opposite direction, keeping the process to be in thermal equilibrium all the time. That's why it's reversible. And now I have refrigerator. So it's going to take, so this is the engine. So I'm going to take 40 joules and give it to it. In doing so now, since it's a reversible process, by the way, it's going to take 160 joules from the cold source and dump in it. So it's the whole process now is reversed, okay? And dump 200 joules to the hot source. So all I did was take this engine and reverse everything. So instead of giving heat, it's instead of giving work, it's taking energy in the form of work. Instead of basically dumping heat to the cold source, it's taking heat from the cold source, this 160 joules, and instead of taking heat from the hot source, it's dumping the 200 joules to it, and now it's working as a refrigerator basically. Now what I'm going to do, you could probably guess it right now, I'm going to connect the two engines, I mean your engine, to this refrigerator and have them operate next to one another. In other words, the 40 joules that you get from your engine, I'm going to straight put it in this refrigerator. Connect the two basically machines together, and now this is what I have, the net effect in here. I have 60 joules dumped to the cold source, but I'm taking 160 joules out of it. So I really have a net take of 160 minus 60, so I'm taking 100 joules from this one. This too will cancel because I'm taking 40 joules from your engine and putting it in this refrigerator, so it's going to cancel, okay? But I'm taking 100 joules from your process, from the engine that you have invented, but I'm dumping 200 joules, so I'm actually taking 100 joules, 200 minus 100, it's 100 joules in here. Close this two in a big box that you can't see now, nobody can see, and now all of a sudden what I have is, I have a process that seems to do the following. That takes, so this is TC, this is CH, that takes 100 joules from the cold source and dumps it completely into the hot source. And this process now can go forever and stopped. Since you claim that that works, and this is a reversible process, so this is basically Carnot cycle. So this is not possible. This violates the second law of thermodynamics, the way Mr. Carnot stated it. So there is no natural process, no process that you can take heat from a cold source and dump it to the hot source. Therefore, since this is not possible by virtue of the second law, and since this is a reversible process, there is no problem for it, then your claim is not true. Which means that you cannot have a 40% efficient engine if Mr. Carnot has already found to be 20% efficient. The most you can have is 20% efficient. You cannot have more than that. Obviously, if you came up with, let's say, for example, 30% efficient, not 40% efficient, it can always come with a fraction of this engine and combine it with this one and take your 30 joules and put it in here, and it's still going to give me a net take of heat from the cold source and dump it to the hot source, and that's not possible. So this is the proof that you cannot do that. I know this one ran a little bit longer than I was hoping to have it. So this is part one. So let me stop into this case in here, and I'm going to come back in here. What I'm going to do in this case, we're going to talk about the entropy, because it's a key concept in here. and we're going to calculate the entropy for at least the calorimetry process. And then I'm going to do problem 56 in class, actually in lecture first. Problem 56 from this chapter, because it's the Stirling engine. It's part of a demo that I have for you guys. So I'm going to do the Stirling engine, but then I have problems 34, 42, 34, 42, 52, and 53. Those are going to be part of a separate video. Okay, so I'm going to pause it in here.